All right, hello everyone. Today we're solving LeetCode 104, maximum depth of a binary tree. Given a root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So if we look at this first example here, in order to solve this, we have to know first what's a root node. A root node is the first node in the tree. And what is a leaf node? A leaf node is any node in a binary tree that has 0 children. So that would be 9, 15, and 7. Now, what we want to do is find what's the longest path. So let's check the first path. From 3 to 9, that's only 2 paths, or 2 nodes in that path. From 3 to 20 to 7, that's 3 nodes in that path. And 3 to 20 to 15, that's 3 nodes in that path. So that means that the longest path from the root down to the farthest leaf would be 3. Therefore, the maximum depth of this binary tree is 3. All right? So now that you understand what the problem's asking for, we can get into the approach. Today we're going to be using a depth first search algorithm, and I'm going to quickly explain what we're going to be doing, and then we're going to get more in depth. No pun intended. So we're going to do a DFS on the left and right of every node's subtree, and what we want that DFS to return is the number of nodes in that subtree, and then we just add 1 for the current node that we're at, and we keep returning up until we get to the root, and then that will give us the maximum depth. So I'm going to quickly explain and walk through how we do this. So let's say we start at 3 in DFS. We always go DFS node.left first. So we go .left, and now we're at the 9. 9 goes .left, and this will be our base case. When we hit a null node, then what we want to do is return 0, because that means that there are 0 nodes to the left of 9, but the program doesn't intrinsically know that, so we have to make sure we return that. So we want this to return plus 0, or just maybe a 0 there. Now we go DFS node.right, and we have a 0. All right, perfect. So now we see we're at 9, and 9 now knows what the right and left subtrees contain. So now all we have to do is return the max of the left and right plus 1 for the current node. So the max of 0 and 0 is 0, obviously, plus 1 because we have to count for 9. So that means that 9 returns up to 3 and returns 1 because the max of the left and right is 0 plus 1 for the current node. Now we do the same thing on the right side. So we go DFS node.right, .left, and this is the base case, so return a 0. We do the same thing on the other side. .right, base case, return a 0. And we say, what's the max of the left and right subtrees? We say, oh, well, it's 0. 0 plus 0. 0, the max of 0 and 0 is 0, plus 1 for the current node, so that will be 1. So that means that 15 returns up to its parent node 20, the number 1, because there's 1 node. As you can see, the left subtree from 20 has 1 node, and that's why 15 returns 1 to let 20 know that there's only 1 node here. Now we do the same thing on the right-hand side. We go down to the 20, and for completeness sake, I'm going to make sure I do all of the calls. Both of these will return 0. So 0 here, 0 here. The max of 0 and 0 is 0, plus 1. So that means that 7 returns up to its parent, a 1. Now, here's the fun part. We do the same thing for 20. So what's the max of 1 and 1? It's 1, plus 1 for the current node. So that means we return up 2 to its parent node. And I just want to quickly go back to this node 20 here to make sure everyone's on the same page. Why do we return up 2? And why is the max 1 and 1? You see, so the left subtree has 1 node, the right subtree has 1 node, and we don't want to take both of them. We just want to take whatever is the biggest because we're looking for the longest path. So that's why we use the max function in Python to take whichever one has the longest path. Since they're the same, it doesn't matter. Just like when we saw the answer, we could either take 3, 20, 15 or 3, 27. So it doesn't matter which one we take, but I just want to clarify that. And now lastly, when we're at 3, now 3 knows what's on the left side and knows what's on the right side. So we see what's the max of left and right. We say, well, it's 2 because 2 is larger. And we need to add the current node. So 2 plus 1 equals 3. And we'd return 3. The answer would be 3. And if we go back here, we see the answer is 3. And that's how we solve it. So let's quickly go into how we code up a solution like this. first. Let me zoom in so people can actually see. It's always a helpful bit. All right. So when you're solving a problem like this, you need to assume that the interviewer or the problem test cases can give you a test case where there is no nodes at all. What if they give you an empty binary tree? So we say if not root return 0, because the depth would be 0 because there's no nodes. All right, so let's actually get into the real function. So we want to define a function called DFS, and it's going to take in a node as a parameter. And since DFS is a recursive function, we need to have a base case. So if not node return 0. So if we reach a null node, return 0. So just like when we're at the 9 and we go down to null, it returns up 0. So that's exactly why we have this. Next, we want to create our left and right variables. So left equals DFS node.left. And we're going to do the same thing for right. Right? So now these left and right variables will hold what's on the left and right side. So in this case, it would be the left would represent 0 and the right would represent 0 if we were looking from the 9. Now, you can pause the video and continue and see what you think the answer would be, but we need to return the max of left, right, plus 1. Because as you remember, let's say we're at 9, we need the max left and right, so the max of 0 and 0 is 0, plus 1 for the current node, so that's why 9 returns up 1 to the 3, because we have this nice little plus 1 here. And that's actually the whole entire algorithm. So we come out of this function, and all we need to do is return whatever this function call returns. So return DFS root right there, and let's try it out. All right, perfect. And we actually solved the question. It's actually pretty good. So I have a quick follow-up question for you if you're still here, and I want you to comment down below why this happens. So if I remove the plus 1 and add a plus 1 to the left, a plus 1 to the right, and submit it, why do we still get the correct answer? So can someone please comment down below and tell me, how is the counting different? Does the algorithm change? And if not, if it does, tell me why. And if not, just say no. Well, so anyway, that's the end of the video. And I will be making a follow-up video on how to solve this question with breadth first search. So if you're interested in that, click the video in the description, or I'll pin it somewhere around here. Anyway, have a good rest of your day. Peace.